Hello and welcome to today's lesson in numerical analysis. We are going to make series of videos and we are going to discuss numerical integration. Okay, so we'll go through these three rules: the Trapezium Rule, Simpson's 1/3 rule, and Simpson's 3/8 rule. Okay, we make series of videos to go through this and make it very simple for you to understand. So, why is numerical integration important? So, we have functions that we integrate them. Okay, so for instance, if I should ask you to integrate a function like this, it's very simple to do that, right? So, this will give you s squared over 2 plus c. But there are some functions that it is very, very difficult and tedious to integrate them. And most of the times, we can't use the analytic ways we have to integrate some functions. So that is when we employ the use of numerical methods to do that. So we have three rules for doing that. We have the Trapezium rule, the Simpson's 1/3 rule, and the Simpson's 3/8 rule. Okay. So in this first video, we'll go through the Trapezium rule. Okay. So let's take an intro. Integration is just the process of measuring the area under a function plotted on a curve. Okay, and one thing that you have to know is that integration and summation, they are related. Okay, so this thing summation and this thing integration, they are related, but the only difference is that summation is for discrete numbers and we use integration when it is continuous. So for instance, we can sum from x starting I starting from 1 to, let's say, 3, and we can integrate s from 1 to 3, right? So you can see that with this, that means you are going to have s1 plus s2 plus s3, right? That's with the summation. So you can see that with that one we have discrete points, discrete numbers. But when it comes to this, our interval is 1, 3, and with this it is continuous. Every point between 1 to 3 is inclusive. So when it is discrete we sum, when it is continuous we integrate. So that's the relation between the summation and the integration. Okay, so when you talk about integration, it's just a process of measuring the area under a function plotted on a curve. So let's talk about the trapezoidal rule. It's the same as the trapezium rule. Okay, so we'll first talk about the single segment, and after that we'll extend it towards multiple segments. So the trapezoidal rule is based on the Newton code formula, which says that if one approximates the integrand, okay, so when you have this thing, let's say integral from a to b, f of x dx, okay, a, b are our limit of integration. So this f of x, the function f of x, is what we call the integrand. So when we approximate the integrand by an nth order polynomial, then the integral of the function is approximated by the integral of that nth order polynomial. Okay, so that means that this integrand here, we can approximate it by an nth order polynomial. Let's say a first order polynomial, a second order polynomial, or something like that, and we use that for our calculation. Okay, so let's take this figure here. Okay, so you can see that we have 2 points, a and b, right? And So we have a curve. You can see we have a curve here. Alright. We are supposed to find the area of this curve. Is somehow complicated to do that. So we want to use approximate that function by a first order polynomial to do that. So we draw a line here, and we also have these 2 points A and B. So the functional value here will be f of A, that here will be B. Okay, so this figure is not drawn to scale, but the figure we get here is a trapezium. Okay, so we are going to derive the formula for the single segment Simpson's 1/3 rule, and we are going to use two methods, by geometry and using calculus. Okay, so by geometry we know that the area of a trapezium is given by half times height times the sum of the parallel sides. Okay, so looking at this diagram here, our height is b minus a, and our parallel sides are f of a and f of b. So this will be our height, and this will be the sum of the parallel sides. Okay, all right. So we have the area is equal to 1 over 2 b minus a times whatever we have here. So just this is just this, right? It's the same thing. Okay, so this is the formula for computing the area of that curve when we approximate the integrand by a first order polynomial. Okay, so this is the formula for the Simpson's 1/3 rule when we have a single segment. So a single segment means that our n is just 1. Do you get it? You can see that we had a point A, we had a point B. We just have one segment. So it makes it what? A single segment for the trapezoidal rule. So let's derive it and go through the derivation. So we derive the trapezoidal rule from calculus, okay? And this will make you understand it better. So we have this here, and this is a problem we want to solve. So we are supposed to integrate f of x dx from a to b. But let's say this function f of x that we have, it is very difficult to use analytic methods to do the differentiation. So we want to approximate it by a first order polynomial. You know, when it comes to the trapezoidal rule, the trapezium rule, we always approximate the integrand by a first order polynomial. You realize when you go to the Simpsons 1/3, we use a second order, and the Simpsons 3/8, we use a third order polynomial. So for the trapezoidal rule, we use a first order polynomial. Okay, so we want to approximate f of x by a first order polynomial, say p1 of x. Okay, think. All right, so that means this here we are approximating it by this. So you can see the only difference here is the integrand. We are approximating it by a first order polynomial, which we are calling p1 of x. So since p1 of x is a first order polynomial, it is given of this form. I hope you remember from your interpolation. Okay, alright, so making substitution, then we are going to have the integral from a to b f of x ds will be equal to integral from a to b. Now p1 of x is what? a0 plus a1x dx. So you can see it is very simple to what? Integrate this function. So when we integrate this function, we will get a0 x plus a1 s squared over 2. Then our limit of integration ab. Alright. So when we put in the first limit b, we would have this part. and the second limit will give us this part. So when we try expanding, then we have a naught b, right? So here minus a naught a plus this plus a1 over 2b squared minus a1 over 2a squared. Then you can see that here we have a naught, so we can bring that one out. Then here we have a1 over 2, a1 over 2, so we can bring that one out, and that will give us this. I hope we get it. So we call this equation A. So after getting this, the only thing that we need to find for is we need to find for our a0 and a1. So that means we have to create systems of equation and solve them simultaneously to get values for a0 and a1, so that we can make our substitution back into equation A. So from, we had p1 of x, right, equals a0 plus a1 of x, right? So for convenience sake, let's change the p1 of x to f1 of x. It doesn't change anything. Okay, all right. So that is why you can see from f1 of x is equal to a0 plus a1 of x. We've just changed the p to f. So we know we have 2 points a and b. So we take the first point a at x equals a. That means wherever you find x, we put a there. So we get f of a will be equal to a0 plus a1a. We call this equation 1. Then at x equals b, we will have f of b will be equal to a0 plus a1b. And we call this equation 2. So you see now we have two equations containing a0 and a1. So we can solve these two equations simultaneously to find values for a0 and a1. So these are the two equations we have. So we are coming to solve it. So this is equation 1 and this is equation 2. So equation 2 minus equation 1 will give us f of b minus f of a equals, a0 minus a0 will give us 0. So we get a1b minus a1a. And then since a1 is common, we can factorize that one out and we have this. Then from here we can easily find for a1 by dividing through by b minus a. So when we do that, then we get a1 will be equal to f of b minus f of a all over b minus a. And this is a1. So we have to substitute this into one of the equations to get what? a0. So we substitute a1 there. We had a1 to be there. So we substitute that into what? Equation 1. So that will give us f of a will be equal to a0 plus a. Wherever you find a1, we put this one there. Then we multiply through by a. And that gives us this. So when we get this, since we are interested in a0, we can send this to meet this guy here. So that's the same thing as this. So we have a0 equals f of a minus whatever we have here. Okay. Then with the right hand side, we can decide to multiply f of a by b minus a, so that the LCM for that whole side will be what? B minus a. So that's what you can have here. Okay. So when we get here, then we try to expand this part. So we get b f of a minus a f of a. Right? Then we have that side. So when you get here, can you see something interesting is about to happen here? So you see that this will cancel this. Then we just be left with b f of a minus a f of b all over b minus a. And that is going to be a0. So now we have a0 and we've found a1. So we come back to equation a. Do you remember equation A? Okay, so we come back to equation A, there's it. And we put in A1, A0 and A1, okay, inside our equation. And that'll help us to derive our formula. So now we substitute A0 and A1 back into equation A. And you've forgotten, this was equation A. So where you find A0, we put this there. Where we get A1, we put this there. So now the next thing left is for us to do simplification, okay? Alright, so you see with here, it's very simple. This will cancel this. Then we'll just be left with b f of a minus a f of b. Then here, this thing here, difference of 2 squared. So we can write it in this form. B plus a, b minus a. I hope you get that. Yes. Alright, so when you write it in this form, then this will take this away. Then we'll be left with this thing here. Hope you get that. Alright. So then the next thing for us to do is just to expand this parts of it. So expanding that will give us bf of a minus af of b plus half bf of b minus half bf of a plus half af of b minus half ef of a. So when we get here, let's see, something interesting will happen. This and this, right? They are the same. So you're going to get bf of a minus 1 over 2 bf of a. So we just take half from this, and that will give us 1 over 2 bf of a. Okay, all right. Then when it comes to this one, to this, we have minus a f of b, and we have plus half f of b here. So that one will give us minus 1 over 2 a f of b. Then the rest will be maintained. It is very interesting and it's very simple when you follow. Okay, so when we get here, then what we can do is that we bring all the ones containing b to one side and all the ones containing a to also to one side. So you see, this one contains b, this one contains b. So you have 1 over 2 b out, f of a plus what f of b. That's what you can see here. Then here too, this contains ef of a, and this contains ef of b, but they all have a and what a. So we bring minus 1 over 2 a out, and we have f of a plus f of b. I hope you get that. So you get how we got this. And since these two, so we are using our algebra that we learned. So since these two are the same, you can see f of a plus b, f of a plus b. Then that means we can simplify this equation to get 1 over 2. So you see we have 1 over 2b minus 1 over 2a. Then all times f of a plus f of b, right? So this is what we have brought the 1 over 2 out, and we have this. We have our f of a plus f of b. So finally we have our formula. It's interesting, right? But don't worry, if you didn't get any, you can always go over the video and you realize that the understanding will come. Okay, so if you got that, then let's solve a question with it. Okay, I'm sure you might have seen this question somewhere. It's very simple. So it says the vertical distance covered by a rocket from t equals 8 to t equals 30 seconds is given by what we can see here. Have you realized that this function looks a bit complicated, and integrating it analytically is going to pose some challenge? So you see, that's the reason why we employ numerical methods to do such integration for us when our integrand is somehow difficult to integrate using analytical methods. Okay, so the question says use a single segment. So you take note of the single segment trapezoidal rule to find the distance covered from t equals 8 seconds to t equals 30 seconds. Okay, so let's solve this question. So the formula for a single segment trapezoidal rule is given by integral from a to b f of x dx equals 1 over 2 b minus a, then f of a plus f of b. So with this question, this is going to be our f of x. Can you see that? And our lower limit was 8, so that's a. And our upper limit was 30, that's b. So we just have to make substitution. So f of a will be equal to f of 8, right? So here, let me see, since it's a function of t, let's do it f of t. Okay. So here f of a will be equal to f of 8, and which is equal to 177.27. So wondering how we got this value, this is how we got it. We will take the f of t, then wherever we find t, we put what 8 there. So we will put 8 here and put 8 here as well. And you compute that from your calculator into 2 decimal places, it will give you 177.27. Then f of b, which b is 30, which is f of 30, will give you 901.67. So with that one, wherever you find t, you put 30 there. So now you know what your b is, what your a is, what your f of a is, what your f of b is. So you come back here and put it inside this formula. Okay, and that will give you the answer you are seeking after. So that means this integration will be equal to 1 over 2 b is 30 minus a, which is 8. This is f of a and this is f of b. So evaluating this gives us this result here. So that's how we do this integration, and have you seen it is quite simple, right? So if you understand this, then let's now direct our focus to the composite or multiple segment trapezoidal rule. Okay, so you see, so far what we did was just for when we have one segment, but we have errors. Whenever we are doing approximation, we have errors. Okay, and the truth is that when you use just one segment, your error is a bit huge, but as you increase the number of segments, it reduces the error. Okay, so sometimes you can be asked to use 2 segments, 3 segments, 5, and the rest. So when you have multiple segments, how do we apply our trapezoidal rule? That is what we are discussing next. So this is when we decide to divide our interval AB into n equal parts. So equal, it should be equal parts, where n can be 2, 3, to any natural number. When n is 1, then we have the single segment. That's why we are starting from 2. So it says note, using the multiple segment reduces the true error, as I said, as it increases. That means if you use more segments, the error decreases. Okay, so the generalized formula then becomes, so the area we are trying to find is equal to h over 2 f of a plus 2 summation from 1 to n minus 1 f of a plus ih plus f of b. where h is equal to b minus a over n, where n is the number of segments. Okay, so don't worry, we will explain this. Okay, so for instance, let's say if we have this, so you see now we have AB, we have just one segment. So if we decide to divide this into two segments, two equal parts, that means what we have here will be A plus B over what? 2. Alright, so using this formula, we'll have A will be equal to H over 2, then F of A plus 2 F of A plus B over 2. That's the point here. Then plus F of what? B, where H will be B minus A over N, which is what? 2. Okay, so that's how we use it. But let's use that to solve an example and the understanding will be even better. Okay, so it says evaluate this integral. So integral from 1 to 2, 1 over x dx, using the trapezoidal rule with 5 segments. So that means n is equal to 5. So this is what it means. We have to take this interval 1, 2 and divide it into what? 5 equal parts. Okay, so you see h is given by what? B minus a over what? N, and our b is 2, our a is 1, n is 5. So 2 minus 1 over 5 is 1 over 5, which is 0.2. So that means I will be stepping by 0.2. So 1.2, 1.4, 1.6, 1.8. So let me bring mine 2 here. So that's it to be equal width. Okay. So how many segments do we have? 1, 2, 3, 4, 5. So we have 6 points. So using a trapezoidal rule with 5 segments, that means the formula will be given by, so this is what we just did, right? So the formula will be given by integral from 1 to 2. Oh, how can it be 1 to 2? So integral from 1 to 2, no, we wrote it the opposite. 1 over x will be equal to h over 2 f of 1. That's the first, you see, 1 is the first one, and the last one is what? F of 2. So the rest are interior. There will be twice of them. So twice of f of 1.2 plus f of 1.4 plus everything. Can you see that? It's very simple. So the end point is just 1. The starting point is, you just multiply by 1. Then the rest in between the first and the last to be twice of them. Okay. So now let's compute our f of 1 to f of 2. So you know f of x is equal to 1 over what? X. So that means f of 1 will be 1 over 1, which is 1. F of 1.2 is 1 over 1.2, which is 5 over 6. F of 1.4, 1 over 1.4, which is this. F of 1.6 is this. F of 1.8 is this. And f of 2 is this. Okay. Alright. So hence, our integral will be integral from 1 to 1 over x dx will be equal to h. And you know, we had h to be 0.2 when we computed it. Okay. We have 0.2 over 2 because it is h over 2. Then f of 1, which is 1, plus twice f of 1.2, f of 1.4, f of 1.6, f of 1.8, then plus what? F of 2. So you just make substitution. So if you compute this, it gives you 0.696. And that happens to be the solution we were working towards. So this is everything about the trapezium rule. Okay, so you can better your understanding by trying your hands on several questions on them. But trust me, it's not difficult at all. So thank you very much. I know this video has been a lengthy one, but I'm sure you've also learned a lot. Okay, so I'm Boydukan Randolph, a final year student of mathematics at the Kwame Nkrumah University of Science and Technology, Ghana, West Africa. So in our next video in this series, we will talk about the Simpson's wanted rule. So with that one, we are going to approximate the integrand by a second order polynomial. You know, with the trapezoidal rule, we approximated the integrand by a first order polynomial. So see you in the next video.